Before we begin, we need to know when to use ice tables. So if the problem gives you an initial amount or initial concentration, that is when we use ice tables. I stands for initial concentration, C stands for change in concentration, and E stands for equilibrium concentration. Let's complete the ice table by reading the problem. In an empty 5-liter flask, it initially contained 0.350 mole of H2. Remember that concentration is equal to moles divided by liters, so when we do 0.350 divided by 5 liters, we get the initial concentration of H2, and that will be 0.0700. We have 0.500 moles of I2 at initial as well, so 0.500 divided by 5, we get the initial concentration of I2 of 0.100. At equilibrium, I2 is equal to 0.040 moles per liter. This is the equilibrium concentration value. It tells us it's at equilibrium. We have 0.040 for I2. It doesn't tell us the initial value of HI, so we assume it is 0. Initial plus change is equal to equilibrium, so we can get change by isolating it. Change is equal to equilibrium minus initial, so when we do 0.040 minus 0.100, we get a change of negative 0.060, and the change will be the same for everything. H2 is on the same side as I2, so we'll have a negative change of 0.060. Initial plus change is equal to equilibrium, so you have 0.0700 plus negative 0.060, and that will get us the equilibrium value. HI is on the other side, the product side, so it will have a positive change of 0.060. However, it has a coefficient of 2, and coefficients multiply the change, so we have 2 multiplied by 0.060. Now, the reasoning behind this is, in terms of shifting, how does H2 and I2 decrease? Well, shift right will decrease H2 and I2, but it will also increase HI. Initial plus change is equal to equilibrium, so 0 plus 2 multiplied by 0.060 will get us 0.12. Now we write the equilibrium constant expression. Kc is equal to products divided by reactants, so we have HI to the power of 2, since it has a coefficient of 2, divided by H2 and I2. Plug in the numbers available, specifically the equilibrium concentration value, so we have 0.12 divided by 0.0100 multiplied by 0.040. Using your magnificent calculator and calculating this out, you should get a value of 36, and that will be the answer to this question. This question has the same process as the other one, so you can pause the video and try this yourself if you would like. 0.800 moles of HBr was placed in a 1.50 liter container, so placed is another way to say initial. So we're going to have to use an ice table for this. So we have a 150 liter container. Remember that concentration is equal to moles divided by liters. So if we do 0.800 divided by 1.50 liters, we can get the initial concentration of HBr, which will be 0.533 rounded. At equilibrium, H2 is equal to 0.120 moles per liter, so this is the equilibrium concentration value for H2. It doesn't tell us the initial value of H2 and Br2, so we assume they are 0. Initial plus change is equal to equilibrium, so change will be equal to equilibrium minus initial. 0.120 minus 0 will get us positive 1.20. Anything that has an initial concentration of 0, it will always have a positive change, because if you think about it, if you get a negative change, you're going to get negative answers, and that makes no sense. Since Br2 is on the same side as H2, it will have a positive change of 0.120 as well, and we know 0 plus 0.120 will get us the equilibrium value, and this would just be 0.120. HBr is on the other side, the reactant side, so we have a negative change of 0.120, and it has a coefficient of 2, so the 2 will multiply the change. Initial plus change is equal to equilibrium, so 0.533 plus negative 2 times 0.120 will get us the equilibrium value. Now that we have all the equilibrium values, we're going to write the equilibrium constant expression Kc. Kc is equal to products divided by reactants, so we have H2 multiplied by Br2 divided by HBr to the power of 2, since it has a coefficient of 2, and we plug in the numbers we have available. So we have 0.120 multiplied by 0.120 divided by 0.293 to the power of 2. Using your calculator and calculating this out, we get a Kc value of 0.167. If you got 0.168, it's because you used rounded answers, but if you use exact answers, you get 0.1673, which means you do not round it up. Let's tackle this next problem. A 4-liter flask contains 0.800 moles of nitrogen. Contained means it was at an initial, so that means we need an ice table. Remember that concentration is equal to moles divided by liters, so we have 0.800 divided by 4 liters, and this will get us the initial concentration of N2, which is 0.2. We also have 0.800 moles of oxygen. 0.800 divided by 4 liters will also still get us 0.2. It doesn't tell us the initial concentration of NO, so we assume that it is 0. And then find the equilibrium concentration of all the gases. So this is all the information we have, so we must put a variable in for C and E to complete the ice table. So let's use X. Remember that whatever side has an initial concentration of 0, it must have a positive change, because if it doesn't have a positive change, we're going to get negative answers. And coefficients multiply change, so we have positive 2x. For O2 and N2, they are on the other side, the reactant side, so they will have a negative change, no coefficients that are multiplying the change, because their coefficients are just 1. Equilibrium is equal to initial plus change, so we do 0.2 plus negative x, that's 0.2 minus x, and then we have 0.2 minus x as well. 0 plus 2x is just 2x. Now that we complete the ice table, we can write the equilibrium constant expression. So we have Kc is equal to products divided by reactants. So we have NO to the power of 2, since it has a coefficient of 2, divided by N2 and O2. And now we plug in the numbers available. We have the Kc value, which is equal to 0.100, and then that is equal to 2x to the power of 2 divided by 0.2 minus x multiplied by 0.2 minus x. We can write this in a better way, since 0.2 minus x multiplied by 0.2 minus x is just 0.2 minus x squared, and you should see that we can take the square root of both sides. If we take the square root of this side, we have to do it to this side. After we take the square root of both sides, we are left with the square root of 0.100 is equal to 2x divided by 0.2 minus x. Taking the square root of a number that is being squared just gets rid of the exponents. And now we want to move 0.2 minus x from the denominator to the numerator, so we can isolate x, so we can move 0.2 minus x diagonally. And what that does is we get the square root of 0.100 multiplied by 0.2 minus x is equal to 2x. Square root of 0.100 is going to get FOILed into 0.2 and minus x. And when we do this, we get square root of 0.100 multiplied by 0.2 minus square root of 0.100. X is equal to 2x. We want to move the x to the other side, so we need to add square root of 0.100 x to this side. Whatever you do to one side, we have to do to the other side. So 2x plus square root of 0.100 x. And you should see that we have negative square root of 0.100 x plus square root of 0.100 x, and this will cancel out. After doing this, we are left with the square root of 0.100 multiplied by 0.2 is equal to 2.32x. We got this by combining like terms. You can combine coefficients as long as they have the same variable and it's to the same degree. To isolate x, we divide by 2.32. And then what we do to one side, we have to do other. So we divide square root of 0.100 multiplied by 0.2 divided by 2.32. Using your calculator and calculating this out, you should get an x value of 0.0273. Now that we have the x values, we can find the equilibrium concentration of all the gases. We set the equilibrium concentrations of N2 and O2 is equal to 0.2 minus x. So we do 0.2 minus x value we got, and that gets an answer of 0.173 moles per liter, rounded. And we said for NO, it is equal to 2x. So 2x, we just multiply the x value you got by 2, and that gets us 0.0546 moles per liter, rounded. So for questions in which they don't give you enough information to complete the ice table with numbers, you're going to have to use a variable to solve the question. As long as you have Kc, you can solve for the variable. This next question is very similar to the last one, so you can pause the video and try this yourself, or you can work along with me. So if 0.300 moles of SO3 gas and 0.300 moles of NO gas are placed in an empty 1 liter vessel, so these are the initial amounts, right? It's in an empty 1 liter vessel. So we know we need to use an ice table. Concentration is equal to moles divided by liters. But since we have 1 liter, it won't really do anything. So the initial concentrations SO3 and NO gas are just 0.3. Determine the equilibrium concentration of SO3 gas and SO2 gas. So it doesn't give us the initial concentrations of NO2 or SO2. So we assume they're both 0. And that's all the information we have to complete the ice table. So now we're going to have to use variables. Remember, whatever has an initial concentration of 0 must have a positive change. So NO and SO2 will have a positive change of x, and that means they will have an equilibrium value of just x, 0 plus x. SO3 and NO are on the other side, the reactant side, so their change will be negative x, no coefficients, so it won't multiply the change. 0.3 plus negative x, which is 0.3 minus x, will get us the equilibrium values. They both are the same, so 0.3 minus x will be their equilibrium values. Now that we completed the ice table, we can write the equilibrium constant expression. Kc is equal to products divided by reactants. So we have NO2 multiplied by SO2 divided by SO3 multiplied by NO. Plug in the numbers available. We have the Kc value is 0.200 So 0.200 is equal to x multiplied by x divided by 0.3 minus x multiplied by 0.3 minus x. We can write this in a better way in which the numerator will be x squared, because x multiplied by x, and 0.3 minus x multiplied by 0.3 minus x can be written as 0.3 minus x squared. You should notice that we can square root both sides, so we can take the square root of this side, and that means we take the square root of the other side. When we take the square root of both sides, we are left with the square root of 0.200 is equal to x divided by 0.3 minus x. The square root got rid of the exponents. Now to isolate x, we want to move 0.3 minus x up, so we move it diagonally up. And when we do that, that means square root of 0.200 will multiply by 0.3 minus x, and this is equal to x. The square root of 0.200 will FOIL into 0.3 minus x, and when we do that, we get the square root of 0.200 multiplied by 0.3 minus square root of 0.200 x is equal to x. Now we want to move x to the other side, so what we have to do is we have to add the square root of 0.200 x to this side. Whatever we do to one side, we have to do the other, so x plus square root of 0.200 x on this side. Negative square root of 0.200 x plus square root of 0.200 x will just cancel out. After doing that, we get the square root of 0.200 multiplied by 0.3 is equal to x plus square root of 0.200 x, in which we can combine like terms and get 1.45x rounded. To isolate x, we need to divide this by 1.45. We need to divide the other side by 1.45. And using your calculator and calculating this out, you will get an x value of 0.0927. Now that we have the x value, we can determine the equilibrium concentration of SO3 gas and SO2 gas. For SO3, we set the equilibrium concentration as 0.3 minus x. So when we do 0.3 minus x, we get 0.207 moles per liter. And for SO2, we set the equilibrium concentration as just x. So SO2 is just equal to the x value of 0.0927 moles per liter. Don't forget the units. Let's tackle this next problem. How many moles of HCl is required? Required means it's asking for the initial amount of HCl, so that means we need to use an ice table in a 1.00 liter container to produce 0.600 moles of Cl2 at equilibrium. Concentration is equal to moles divided by liters, so 0.600 divided by 1, which won't do anything, is the equilibrium concentration value for Cl2. So we have 0.6. And since it's saying we produce Cl2, the assumption is we had no Cl2 in the beginning. Remember that initial plus change is equal to equilibrium, so 0.6 minus 0 will get us change, and that would just be positive 0.6. H2 is on the same side as Cl2, so we're assuming that H2 needs to be produced as well. So it will have an initial of 0. The change will be positive 0.6 as well, and the equilibrium will just be 0 plus 0.6, which is 0.6. HCl is on the other side, so we have a negative change of 1.2. Since the coefficient multiplies the change, we have 2 multiplied by 0.6, so that's how we got negative 1.2. That is all the information we have to fill the ice table, so we're going to use a variable to fill in the rest. So we can have I for x. Equilibrium is equal to initial plus change, so we have x plus negative 1.2, which is just x minus 1.2. With the ice table complete, now we write the equilibrium constant expression, Kc. Kc is equal to products divided by reactants, so we have H2 multiplied by Cl2 divided by HCl to the power of 2. Since it has a coefficient of 2, plug in the numbers available. We have Kc is equal to 1.00 times 10 to the power of negative 3, and this will be equal to 0.6 multiplied by 0.6 divided by x minus 1.2. To isolate x, we need x in the numerator, so we're going to move x minus 1.2 diagonally up, and then we're going to move 1.00 times 10 to negative 3 diagonally down. So we move this up, now we get x minus 1.2 to the power of 2 is equal to 0.6 multiplied by 0.6 divided by 1.00 times 10 to negative 3. What you should notice is that we need to square root the x value, and then what we do to one side, we need to do to the other. After we square root both sides, we are left with x minus 1.2. Since the square root of x minus 1.2 squared just gets rid of the exponent, is equal to the square root of 0.6 multiplied by 0.6 divided by the square root of 1.00 times 10 to the negative 3. Now we need to isolate x, so we're going to add 1.2 to this side. Whatever we do to one side, we need to do the other. And we should see that negative 1.2 and positive 1.2 would cancel out, leaving us with x by itself. We are left with x is equal to the square root of 0.6 multiplied by 0.6 divided by the square root of 1.00 times 10 to the negative 3 plus 1.2. Using your calculator and calculating this out, you get x is equal to 20.2. Now that we have the x value, we can get the initial concentration of HCl. The initial concentration of HCl is just x. so HCl will be equal to 20.2 moles per liter. But remember that the question is asking for how many moles of HCl gas is required. So to get rid of liters, we need to multiply it by the liters. So moles divided by liters, multiplied liter over 1. However, the volume is just 1, so this won't do anything, so the answer will still just be 20.2. Let's do this next problem. A container initially contains, whenever we have an initial amount, we know we have to use an ice table. So a container initially contains 6.00 m of NO2. M is just another way to write moles per liter. So this is the initial concentration of NO2. We have 6. SO2 we have 3, so we have 3. NO we have 4, so we have 4. SO3 we have 9, so we have 9 for the initial concentration of SO3. Calculate the equilibrium concentrations of NO2 gas and NO gas. This is all the information we have to complete the ice table, so now we have to fill in the rest with a variable, and let's use x. So we don't know whether the change is positive or negative, so what we need to do is calculate the reaction quotient. It's written the same as Kc, and all we do is get the answer and compare it to the Kc value given. Kc is equal to products divided by reactants, so we have NO multiplied by SO3 divided by NO2 multiplied by SO2. The reaction quotient can plug in numbers that are not at the equilibrium concentration, so we can plug in the initial values in. So we have 4 multiplied by 9 divided by 6 multiplied by 3. When we calculate this out, we get a value of 2. Now we just compare our answer to the Kc value given. I like to compare it on a number line where the right side numbers are bigger and the left side numbers are smaller. So the Kc value is 1. This is smaller than 2, so this will go on the left side, and 2 will be on the right side. To go from 2 to 1, we need to go left, so this is a shift left. This reaction will shift left to reach equilibrium, and a shift left points at the reactants, so the reactants increase, and it doesn't point at the products, so the products decrease. So the products will have a negative change of x. Equilibrium is equal to initial plus change, so we have 4 plus negative x, which is a 4 minus x, and then we have 9 minus x for the equilibrium for SO3. The reactants have a positive change of x. Equilibrium is equal to initial plus change, so we have 6 plus x. Equilibrium is 6 plus x. And then we have 3 plus x, so the equilibrium is 3 plus x. Now that we have the equilibrium constant values, we can solve for x. So we already wrote the equilibrium constant expression. Now we just plug in numbers available. So Kc is equal to 1. NO is 4 minus x. And SO3 is 9 minus x. NO2 is 6 plus x. And SO2 is 3 plus x. So we can FOIL the top out. And when we FOIL the top out, we're going to get 1 is equal to 36 minus 4x minus 9x plus x squared. And then we can FOIL the bottom out, and when we FOIL the bottom out, we get 18 plus 6x plus 3x plus x squared. You should see that we can combine like terms, so we have negative 4x and negative 9x, we can combine that. And on the bottom, we can also combine 6x and 3x. So when we combine like terms, we get 1 is equal to 36 minus 13x plus x squared. To isolate x, we're going to want to move this diagonally up, and when we move that diagonally up, what we get is we get 1 multiplied by 18 plus 9x plus x squared is equal to 36 minus 13x plus x squared. 1 will FOIL out to all of this, but that won't do anything, so we're just left with 18 plus 9x plus x squared is equal to 36 minus 13x plus x squared. Now let's move everything to one side. I like the left side, so I'm just going to move everything to the left side. So you're going to have to subtract 36. Whatever you do to one side, we have to do the other side. We have negative 13x, so we're going to need to add 13x. Whatever you do to one side, we have to do the other. And then to get rid of x squared, we're going to have to subtract x squared. Whatever you do to one side, we have to do the other side. And now we just combine like terms. So you can see everything cancels on the right side. So we moved everything to the other side. Positive x squared and negative x squared cancel out. 9x and 13x, we combine like terms. And 18 and negative 36x, we combine like terms. 18 and negative 36 will get us negative 18. And 9x and 13x will get us 22x is equal to 0. Let's write this in standard form because it's easier to read. So we have 22x minus 18 is equal to 0. Now we get the GCF out of this. The greatest common factor is 22 and negative 18 is 2. And that leaves us with 11x minus 9 is equal to 0. We want to isolate x, so we add 9 to this side. Whatever we do to one side, we have to do the other. And you should see that this negative 9 and this positive 9 cancel out. After we add 9 to both sides, we are left with 11x is equal to 9. Don't worry about the greatest common factor. You can just ignore that. Now to isolate x, we need to divide this side by 11, and then we divide 9 by 11. When we do 9 divided by 11 in our calculator, that is our x value. So x is equal to 0.818, rounded to the nearest 3 sigdigs. And now with the x value, we can calculate the equilibrium concentration of NO2 gas and NO gas. For NO2 gas, the equilibrium concentration is equal to 6 plus x. So we just do 6 plus x, and that will get us 6.82 moles per liter rounded. For NO gas, we set the equilibrium concentration value is 4 minus x. So we do 4 minus x, and we get a value of 3.18 moles per liter. Okay, let's do this 2-question practice problem. When equilibrium was established at 25 degrees Celsius, NO2 gas is equal to 0.40 moles per liter. Calculate the equilibrium concentration of N2O4. So we don't need an ice table for this question because we don't have any initial amounts or initial concentrations. So to calculate the equilibrium concentration of N2O4, we're going to have to write the equilibrium constant expression. So Kc is equal to products divided by reactants. So we have NO2 power 2, since it has a coefficient of 2, divided by N2O4. Now let's plug in the numbers we have. Kc is equal to 0.80 and NO2 is equal to 0.40 divided by N2O4, since we don't know what that is. To get the value of N2O4, we need to move this diagonally up, and then that means we have to move 0.80 diagonally down. So we have N2O4 is equal to 0.40 divided by 0.80. And when you calculate this out in your calculator, N2O4 will be equal to 0.20 moles per liter. And we're going to need this value to answer this question. So the next part of the problem tells us the equilibrium reaction above was upset by adding 0.30 moles per liter of N2O4 gas. Determine the concentration of both gases if the new equilibrium is reached at the same temperature. So what this means is that we're having a new equilibrium, and that means our previous equilibrium would be the new initial values. And remember, whenever we have initial values, that means we have to use an ice table to solve the problem. So the initial concentration of N2O4 is what we calculated. We have 0.20. However, we also added 0.30 moles per liter of N2O4, so we have 0.20 plus 0.30. NO2 is just 0.40. This was the old equilibrium value. And that is all the information we have, so we have to plug in variables for change and equilibrium. Now we need to determine which side has the positive or negative change. Remember that when something is being added, you don't point at what is being added, so the shift will be right. A shift right points to the product, so the products increase. That means the change will be positive, and NO2 has a coefficient of 2, so 2 will multiply the change. And equilibrium is initial plus change, so we have 0.40 plus 2x. N2O4 has a negative change. Since a shift right doesn't point at N2O4, equilibrium is equal to initial plus change, so we have 0.50 minus x for equilibrium. Now that we complete the ice table, we can write the equilibrium constant expression. We already wrote it up here, so we can just take that again. Now we plug in the numbers available. Kc is equal to 0.80, so 0.80 is equal to 0.40 plus 2x to the power of 2, and then we have 0.50 minus x on the bottom. It may seem good to square root both sides, but if we square root both sides, we do get rid of the exponent here, but then we get an exponent of 1 divided by 2, and we don't want to deal with that. So we're not going to square root both sides. And to isolate x, we need to move 0.50 minus x diagonally up. And what that will do is we get 0.80 multiplied by 0.50 minus x. And on the other side, we have 0.40 plus 2x multiplied by 0.40 plus 2x. This is the same way as writing 0.40 plus 2x squared. And what you should see is that we can FOIL both sides. So when we FOIL 0.80 into 0.50, we get 0.40. 0.80 multiplied by negative x will get us minus 0.8x. And this will be equal to 0.40 multiplied by 0.40, so we have 0.16. 2x multiplied by 0.40 gets us plus 0.8x. And 2x multiplied by 2x will get us 4x squared. To isolate x, we need to move everything to one side. So let's move the left side to the right side. So we have positive 0.40. So we need to subtract 0.40. Whatever you do to one side, we have to do to the other. So we have 0.16 minus 0.40 as well. To get rid of negative 0.8x, we need to add 0.8x. Whatever you do to one side, we have to do to the other. And you should see that everything on the left side cancels out. And on the right side, we're going to have to combine like terms. After we combine like terms, we get 0 is equal to negative 0.24 plus 2.4x plus 4x squared. Let's write this in standard form. It's much easier to read. So we have 0 is equal to 4x squared plus 2.4x minus 0.24. We could probably factor this, but factoring with decimals is really hard. So let's use the quadratic formula. I like to label what is a, b, or c. So 4x squared is a, 2.4x is b, and negative 0.24 is c. And now we just plug in the numbers. So for A, we have 4, for B, we have 2.4, and for C, we have negative 0.24. So when you plug that into the quadratic formula, you get x is equal to 0.087. The quadratic formula gives you two numbers, and the other number was a negative, but x can't be negative, so we don't use that. For N2O4, we set the equilibrium concentration is equal to 0.50 minus x. So we do 0.50 minus the x value we got, and that gets us 0.41 moles per liter rounded. And for NO2, we set the equilibrium concentration is 0.40 plus 2x. So 0.40 plus 2 multiplied by 0.087 will get us 0.57 moles per liter. And that will be the answer to this question. Let's try this final practice problem. In yellow are tips to help guide us. You can pause the video and try this yourself or work along with me. How many moles of CO2 are required to produce? So since it's telling us how many CO2 are required, that means it wants the initial value of CO2. So we need to use an ice table. And the first thing we do is complete the ice table. So it says we produce 0.40 m of O2. Produce means it's at equilibrium concentration. So we have 0.40 for the equilibrium concentration of O2. Since O2 was produced, that means it had an initial concentration of 0. And since CO is on the same side as O2, we assume it has an initial concentration of 0 as well. That is all the information we are given. So CO2 will have an initial concentration of X since it's unknown, and it will also have an equilibrium concentration of X. Change is equal to equilibrium minus initial, so we have 0.40 minus 0, which would get us 0.40. O2 has an initial concentration of 0, so it must be a positive change. CO is on the same side as O2, so we'll have a positive change of 0.80 as a coefficient of 2, and the 2 multiplies the change. Initial plus change is equal to equilibrium, so we have 0 plus 0.80, and that will get us 0.80. CO2 is on the other side, the product side, so we have a negative change of 0.80 as a coefficient of 2, and the 2 multiplies the change of 0.40. Initial plus change is equal to equilibrium, so we have x minus 0.80, so we have x minus 0.80. Now that we completed the ice table, we write the equilibrium expression. So Kc is equal to products divided by reactants. So we have CO2 to the power of 2, since it has a coefficient of 2, divided by CO to the power of 2, since it has a coefficient of 2, multiplied by O2. So let's plug in the numbers available. We have Kc is equal to 5.0, and then we plug in the equilibrium concentration. So for CO2, we have x minus 0.80. For CO, we have 0.80. And for O2, we have 0.40. To solve for x, we need everything to be in the numerator, so let's move 0.80 and 0.40 diagonally up, and what that does is we get 5.0 multiplied by 0.80 squared multiplied by 0.40 is equal to x minus 0.80, and we can square root both sides. So we have 5.0 being square root and x being square rooted. So after we square root both sides, we get the square root of 5.0 multiplied by 0.80 multiplied by 0.40 is equal to x minus 0.80. The square root got rid of the exponent on our x. To isolate x, we need to add 0.80 to this side. Whatever we do to one side, we have to do to the other, so we add 0.80 here. Negative 0.80 and positive 0.80 will cancel out. Using your wonderful calculator and calculating this out, you should get x is equal to 1.9, and with the x value, we can get the initial concentration of CO2. The initial concentration is just equal to x, so CO2 will be equal to 1.9 moles per liter. However, that is not the answer to the question because it's asking us how many moles of CO2 are required. So we just need moles by itself, and to get that, we do moles divided by liter, multiplied by liters to cancel out. And we are given a volume of 2.0, so we have 2 here. So when we do 1.9 multiplied by 2, the answer will be 3.8 moles.